Pluto, a far-off and baffling smaller planet, was once an individual member of our solar system's planetary family. However, later alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They suggest that this frosty world is on a potential crash course with Neptune. But how could this happen, and what might be the outcomes of such an enormous event? Are we seeing an interesting cosmic phenomenon? Or is there something else to this looming infinite crash? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a previous planet that was downgraded to a dwarf planet partly due to its curious orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is perilously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the warning of a potential dangerous crash between these two planets that could pose an immense threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its convergence with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, resisting what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike the other planets, whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all cooperate in a complicated way. Terms like asymptotic libration and scope libration, along with the VZK oscillation, are part of this puzzle, according to astrophysicists. What's keeping all planets in their orbits is a kind of libration. Regarding Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an extra layer of protection from potential impacts. Another critical factor in this situation is the VZK oscillation. This is named after three researchers, VAV Apple, LV, and Kai, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so strange despite the apparent chaos. This oscillation helps keep Pluto's orbit stable from here on for an extraordinarily long time. The VZK oscillation shows that even though things in space may seem wild and random, certain patterns and rules keep everything in place. All of these parts help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or stray off course. This three-body problem helps in understanding how these orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is actually turbulent, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos under control. Recent computer tests have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a large part in protecting Pluto's orbit. What's more, Saturn helps overall too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an extremely long period, possibly even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are vital in the larger context of the universe for maintaining the order and consistency of celestial bodies' movement. Without these components, the solar system as we know it would be a place of far greater turmoil and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of constant observation and study of these phenomena to better grasp our place in the universe. Investigating the depths of space often leads us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for researchers to figure out how Pluto moves in space. These simulations use intricate math to mimic how Pluto, along with other space objects like Neptune, pull on one another. By adjusting small details in the simulations, astronomers can see how even tiny changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be wild and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. However, despite this chaos, Pluto's orbit remains stable for a long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting large events, especially when they involve chaotic orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have made huge strides in understanding space, the case of Pluto reminds us of how our knowledge of the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite all these complex forces working to prevent such an event from occurring, Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He sees the renaming as not a downgrade, but rather a necessary adjustment to our growing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views the intricacies of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, we must keep in mind the ongoing dynamics of the solar system. If Neptune and Pluto were to collide, the results would undoubtedly be catastrophic. These two worlds, though vastly different in size and composition, would release an enormous amount of energy upon impact. Given that Neptune is a gas giant and Pluto a frozen rock, the consequences of a collision would drastically alter the balance of the outer solar system. We may look to other similar collisions or near collisions throughout history in our universe for context. Such events often lead to the creation of new moons, disruption of planetary orbits, or even the formation of new cosmic structures. The aftermath could be long-lasting, changing the shape of the solar system as we know it. In summary, while the prospect of Pluto and Neptune colliding may seem far-fetched, it raises important questions about the stability and future of our solar system. Through the use of advanced simulations and continued observation, we can keep a closer watch on Pluto's path and its interactions with the other giants of the outer solar system. To further delve into the potential consequences of a Pluto-Neptune collision, it's important to consider the broader context of celestial mechanics and the history of planetary interactions. In the vast expanse of our solar system, the orbits of planets and dwarf planets are shaped by the intricate dance of gravitational forces, which can both stabilize and destabilize these objects over time. The interactions between Pluto, Neptune, and other major planets highlight the delicate balance that exists in the outer reaches of the solar system. These delicate interactions might not just prevent collisions, but can also result in dynamic shifts that alter the course of planetary movements over millions of years. One aspect of these gravitational interactions is resonance. As previously noted, Pluto and Neptune are in a 2:3 orbital resonance. This means that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance is key to preventing a collision between the two planets. The gravitational tug-of-war between them is such that when Pluto gets closer to Neptune's orbit, Neptune's position is carefully timed to ensure that they never cross paths. However, even this carefully orchestrated resonance has limits. The resonance itself doesn't eliminate the long-term risk. Instead, it tempers the potential for a direct encounter by ensuring that both planets' paths are synchronized in a way that maintains an effective distance. In addition to resonance, the eccentricity and inclination of Pluto's orbit are significant factors. Unlike the other planets that move almost in a flat, circular path, Pluto's orbit is highly tilted and elliptical. This means that the dwarf planet is often far from the ecliptic plane, which is the path where most planets in the solar system travel. The tilt and shape of Pluto's orbit create a scenario where, even when it comes close to Neptune's orbit, the potential for an impact remains remote. But this doesn't mean that Pluto's orbit is without risk. The highly eccentric nature of Pluto's path means that slight variations in gravitational forces from other planets could, over time, lead to changes in its orbit, making it more unpredictable. The influence of gas giants, like Jupiter and Saturn, plays a crucial role in stabilizing Pluto's path. These massive planets exert a significant gravitational force, not just on Pluto, but on the entire solar system. Their influence on Pluto's orbit helps to keep it from deviating too far from its current course. Jupiter, in particular, is known for its role in stabilizing the outer solar system. It acts as a sort of cosmic shield, preventing smaller bodies like Pluto from being flung out of the solar system or colliding with other planets. This effect is not only important for keeping Pluto in its orbit, but also for ensuring that the solar system as a whole remains in a relatively stable configuration. Despite the apparent stability of Pluto's orbit, The idea of a collision with Neptune continues to capture the imagination of scientists. If such a collision were to occur, the energy released would be immense. Neptune, a gas giant, contains a vast atmosphere of hydrogen, helium, and methane, while Pluto is an icy world composed primarily of rock and frozen gases. A direct collision between these two bodies would release an enormous amount of heat, potentially causing the vaporization of Pluto and disrupting the structure of Neptune's atmosphere. The impact could alter the orbits of both planets and possibly even affect the stability of other objects in the outer solar system, including the Kuiper belt and scattered disk. From a cosmic perspective, a Pluto-Neptune collision would be a rare and extraordinary event, but the chances of it happening are extremely small given the current understanding of their orbits. The gravitational forces that govern these distant planets act in such a way as to maintain a delicate harmony. Yet, as with many phenomena in space, the future is unpredictable. In the immense timescales of the cosmos, even the slightest disturbances could lead to dramatic consequences over millions or billions of years. What we see as stable today could shift dramatically in the distant future. Moreover, any significant shift in Pluto's orbit would likely not happen suddenly, but would unfold over long periods, allowing astronomers to monitor and possibly predict such changes. The development of more sophisticated space telescopes and advanced computational models means that we may soon have the tools to more precisely track the movement of distant bodies like Pluto and Neptune, which could offer insights into how these orbits evolve over time. Such monitoring could also inform us of other potential risks from other celestial bodies in the future, as the dynamic nature of space means that every object in the solar system influences the others in ways that are still not fully understood. In summary, while a collision between Pluto and Neptune remains highly unlikely in the near future due to the careful gravitational dance between them and the stabilizing forces of other planets, the scenario is nonetheless a fascinating one for astronomers and astrophysicists. It serves as a reminder of the complexity of space, where even objects that seem far apart may have subtle and profound interactions. Understanding these interactions is not just important for predicting future events, but for deepening our appreciation of the forces that shape the cosmos. Through continued observation and study, we may one day uncover new aspects of these planetary relationships that could change our understanding of the solar system forever.